You drop a rock, it falls. Simple. Obvious. Every human who ever lived saw this and knew exactly why it happened. Heavy things fall fast. Light things fall slow. Aristotle said so in 350 BCE. The church said so. Your teacher said so. For 2,000 years, that answer was carved in stone. And then one man in Pisa, between 1589 and 1638, did something nobody expected. He looked at the same falling rock and saw something completely different. Not because he had better eyes, because he learned to think in a way that broke reality open. Galileo Galilei didn't just discover inertia. He had to rewire his own brain to see it. And that mental process, or that brutal journey from one way of seeing motion to another, is what actually changed how we understand everything that moves in the universe. Most people think Galileo just did some experiments and wrote down the right answer. That's not what happened. What happened was years of being wrong, getting stuck, and slowly teaching himself to imagine motion in a way that felt completely unnatural. No force needed to keep something moving. Objects in motion stay in motion forever unless stopped. In 1600, that idea sounded insane. It contradicted everything you could see with your eyes, and Galileo had to fight his own instincts every step of the way to get there. If you value documented history of scientific discovery like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from Stillman Drake's 1979 monograph, Galileo's Notes on Motion, published in the Annali dell'Istituto e Museo di Storia della Scienza in Florence, and from Paolo Palmieri's analysis of Galileo's manuscripts, published in the Archive for History of Exact Sciences in 2005. These are not general textbooks. These are researchers who spent decades examining Galileo's actual notebook pages, his crossed-out equations, his failed attempts, the ink composition to date when he wrote what. They reconstructed not just what Galileo discovered, but how he got there. Now back to the information. 1589. Galileo is 25 years old, teaching mathematics at the University of Pisa. He's ambitious, sharp, and completely convinced he can fix Aristotle. Not overthrow him, fix him. At this point, Galileo still believes the core of Aristotelian physics. Heavy objects have gravity. Gravity pulls them down. Their natural place is the center of Earth. You throw something, it moves because you're pushing it. It stops moving because that push runs out. Aristotle said an object in motion requires a constant force. Stop pushing, it stops moving. Makes sense. Looks right. And young Galileo is trying to work within that framework. He's writing a manuscript called De Motu Antiquiora, which means the older writings on motion. He'll never publish it. He'll abandon it incomplete because he realizes it's got fatal problems. But in 1589 through 1592, this is what he's working on. In these pages, he attacks Aristotle on one specific point. Aristotle claimed heavier objects fall faster than lighter ones in direct proportion to their weight. A rock 10 times heavier falls 10 times faster. Galileo says that's obviously wrong, and he's got a clever thought experiment to prove it. This thought experiment appears in De Motu. Imagine two objects, one heavier, one lighter. By Aristotle's rule, the heavy one falls faster. Now tie them together with a rope. What happens? The light object should slow down the heavy object because it's dragging behind. So the combined system should fall slower than the heavy object alone. But wait, the combined system is heavier than the heavy object alone. So, by Aristotle's rule, it should fall faster. Contradiction. Aristotle must be wrong. Galileo concludes, all objects fall at the same speed in a vacuum. Brilliant argument, clean logic. One problem. Galileo's still wrong about almost everything else in motion. He still thinks objects need force to keep moving. He still thinks motion is fundamentally different from rest. He's fixing one piece of Aristotle while keeping the frame. And that frame is what has to break. Between 1589 and 1592, Galileo conducts what may or may not be actual experiments dropping objects from the Leaning Tower of Pisa. His student Vincenzo Viviani later claims Galileo did this in front of professors and students. Historians argue whether it really happened. Antonio Favaro in 1890 and Stillman Drake in the 20th century suggest it probably did happen, but not as a formal public demonstration. More likely, informal arguments with colleagues and students, showing them, look, these fall together. The tower tests, real or thought experiment, matter less than what Galileo observed when objects fell down inclined planes, because the tower is too fast. Objects fall, hit ground, done. No time to measure anything precisely. No way to see what's actually happening during the fall. So Galileo does something clever. He He builds a ramp, not just any ramp, a wooden beam, 12 cubits long, that's about 7 meters. Half a cubit wide, about 30 centimeters. 3 finger breadths thick, about 5 centimeters. He cuts a groove down the center, lines it with parchment as smooth and polished as possible. Why? To reduce friction. He wants motion as close to pure falling as he can get, but slowed down enough to study. He takes a hard, smooth, very round bronze ball, rolls it down the groove. Now he can see motion happen, but there's still a problem. How do you measure time? This is 1600. No stopwatches, no accurate clocks. Clocks that could measure seconds barely existed. Galileo's solution, a water clock, large vessel of water elevated high, small pipe soldered to the bottom, giving a thin stream. He lets the ball roll a known distance. While it rolls, he collects the water stream in a small glass. Then he weighs the water. The weight of water equals the time elapsed. He does this over and over, different distances, different angles, marking positions on the ramp. Some accounts suggest he used musical beats, humming an Italian march at steady tempo, placing markers where the ball passed on each beat. When spaced correctly, the ball hitting strings stretched across the groove made sounds at even intervals. He's hunting for the pattern. How does distance relate to time? The answer appears between 1602 and 1604. The distance traveled increases as the square of the time. If it takes 2 units of time to roll a certain distance, it takes 4 units of time to roll 4 times that distance. Not twice the time, 4 times. This is the time-squared law. In odd numbers, in the first time interval, the ball travels 1 unit of distance. In the second equal time interval, it travels 3 units. In the third, 5 units. In the fourth, 7 units. 1, 3, 5, 7, 9, 11. Distance equals acceleration times time squared. Galileo wrote this to his friend Paolo Sarpi on October 16th, 1604. The letter survives. It's in the seminary of Pisa. Hi. Spaces traversed in natural motion are in the double proportion of the times, Galileo writes. He's got the right equation, but for the wrong reason. Because in 1604, Galileo still believes speed is proportional to distance fallen, not time. That's a critical error, he thinks. The farther you've fallen, the faster you're going, which sounds reasonable, but it's wrong. The right principle. The longer you've been falling, the faster you're going. Speed increases with time, not distance, and this mistake is going to haunt him. Here's where it gets strange. Galileo derives the correct law of falling bodies from an incorrect assumption. Historians have debated this for a century. How did he get the right answer from wrong physics? The manuscript that survives from 1604 shows his derivation. He reasons, if speed is proportional to distance, then average speed over distance increases with the square of distance. Therefore, time must be proportional to the square root of distance. Flip that, distance is proportional to the square of time. Correct law, wrong foundation. Some historians, like Israel Drabkin in 1960, argue Galileo discovered the law experimentally first. He saw the 1357 pattern with the inclined plane and water clock, saw distances increase by odd numbers in equal times, then tried to work backwards to find a principle that explained it. He grabbed the wrong principle, speed proportional to distance, because it seemed intuitive, and because mathematically it could be tortured into giving him what he'd already observed. But by 1608 RR, maybe 1609, Galileo realizes the error. Something doesn't fit. When he tries to extend his theory to projectiles, objects thrown at angles, the math breaks. His predictions don't match his small-scale experiments, rolling balls off deflectors. This is where the real transformation begins. Not in 1604 when he had the equation, but in 1604 through 1608 when he had to rethink everything. Galileo starts studying projectiles. Balls rolling down inclined planes that then launch horizontally or at angles. He's got pages of data, Folio 81, Folio 107, Folio 114, Folio 116. These notebook pages survive. Researchers in the 20th and 21st centuries analyzed them, measured the data points, reconstructed the experiments, figured out what Galileo was seeing. Ronald Naylor published Key Analysis in ISIS in 1980. Stillman Drake analyzed the folios in multiple papers through the 1970s. The story they piece together, Galileo sees the path is curved, maybe parabolic. He measures horizontal distances for different vertical drops. He's trying to confirm his theory. Horizontal speed decreases as the ball loses the impetus from launch. Except the data doesn't show that. The data shows something shocking. The horizontal speed stays constant. This is 18 years before Galileo publishes it. He discovers it around 1606 to 1608 Horace, buried in experiments nobody saw. The horizontal motion doesn't decay. A ball rolling off a table travels the same horizontal distance per unit time, whether it's at the start of its path or near the ground. Constant horizontal velocity, independent of vertical fall. This is the principle of inertia breaking through. Motion in the horizontal direction doesn't need continuous force. It persists on its own, but Galileo doesn't leap straight there. He's still tangled in old concepts. Impetus, memento. These words appear throughout his notes. Impetus from medieval thinkers, but Galileo uses it differently. Not a force stored in the object, more like a measure of motion's effect, the violence it can cause on impact. He's trying to think in multiple frameworks at once. Aristotelian gravity pulling down, medieval impetus kept in motion, and now this new thing, horizontal motion that just continues. He's at war with himself. Here's what it feels like inside his head around 1606. He rolls a ball down a ramp. It shoots horizontally off the edge. It curves down and lands. He measures where it lands. He tilts the ramp steeper. Same horizontal launch speed if the vertical drop is the same. Shallower tilt, ball rolls longer, builds up more speed, it lands farther, but when he calculates the horizontal speed during flight, it's not changing during the flight. So the motion on the ramp is accelerated motion, gaining speed. The motion through air horizontally is uniform motion, keeping speed. Why? What's the difference? Gravity acts vertically. Nothing acts horizontally. That's the difference. No force, no change in motion. Force, change in motion. This is the seed of Newton's first law, but Galileo can't quite say it that cleanly because he's still half Aristotelian. He still thinks of rest as fundamentally different from motion. He can't commit to the idea that motion is just as natural as rest. That would mean an object shot into empty space would move forever, which seems absurd in 1608. Infinite motion from finite push, how? But the experiments keep saying it, so Galileo builds a compromise concept. On horizontal surfaces, motion can persist because there's no uphill or downhill component. Gravity pulls down, not sideways. So a perfectly smooth, perfectly flat plane with no air resistance would let a ball roll forever. Not because motion is natural, but because there's no reason for it to stop. Nothing opposing it. This is progress. But it's not full inertia yet, because Galileo's still thinking. The ball is trying to roll forever on this plane because the plane is level. He's still thinking there's something special about horizontal. That's wrong. Full inertia says motion in any direction persists. Straight line at constant speed. Period. Doesn't matter if it's horizontal, vertical, diagonal, whatever. No force, no change. But Galileo's not there. He's thinking circular motion for planets, horizontal motion for terrestrial objects. Now we jump to 1632. Galileo's 68 years old. He publishes the Dialogue concerning the two chief world systems. This is the book that gets him in trouble with the Inquisition because it argues for Copernican heliocentrism. But buried in day 2 of the Dialogue is Galileo's ship experiment. This is where the mental breakthrough becomes visible in print. Not in equations, in a thought experiment. He writes through his character Salviati. Shut yourself up with a friend in the main cabin below decks on some large ship. Bring flies, butterflies, fish in a bowl, a bottle dripping water. With the ship at rest, observe carefully. The insects fly equally to all sides. The fish swim indifferently in all directions. Drops fall into the vessel beneath. Throw something to your friend. You need the same force in any direction. Jump with your feet together. You pass equal spaces in every direction. Now have the ship move at any speed you like, so long as the motion is uniform and not fluctuating. You will discover not the least change in all the effects. You cannot tell from any of them whether the ship moves or stands still. This is Galilean relativity. The principle that uniform motion is indistinguishable from rest. No experiment inside a closed room can tell you if you're moving at constant speed or stationary. Motion is relative. This is profound. It says motion and rest are not different states of being. They're just relative descriptions. Something is moving compared to what? The shore? Another ship? The sun? There's no absolute motion or absolute rest in Galileo's world, only motion relative to something else. And if motion and rest are equivalent in this sense, then no force is needed to maintain motion, because motion is no different than rest. They're the same thing from different reference frames. This thought experiment doesn't appear out of nowhere in 1632. It's the culmination of 30 years of Galileo rewiring his intuition. From 1589, when he thought motion needed constant force, through 1604 to 1608, when he saw horizontal motion persist in projectiles. to 1632 when he can finally say, there's no difference between moving smoothly and standing still. No experiment can distinguish them. Therefore, motion doesn't need cause any more than rest does. The dialogue gets him in trouble. He's forced to recant Copernicanism in 1633, threatened with torture, placed under house arrest. He's 69. He'll never leave house arrest. He'll die under it 11 years later, but he's not done. Under house arrest in Arcetri, near Florence, he writes his final and greatest work, Discorsi e dimostrazioni matematiche intorno a due nuove scienze, Discourses and Mathematical Demonstrations relating to two new sciences, published 1638. He's 74, nearly blind. The book is smuggled out of Italy to Leiden in the Netherlands, where the Inquisition can't suppress it. Two New Sciences is where Galileo presents the full structure, the mathematics of accelerated motion, the law of falling bodies derived properly from the right principle. Speed increases uniformly with time, not distance. The parabolic path of projectiles proven geometrically, the principle of horizontal inertia stated clearly. And the method, slowing motion down with inclined planes, measuring with water clocks, using geometry to extend from what can be measured to what must be true in idealized conditions. In day 3, Scias, Galileo through Salviati proves, if a body starts from rest and moves with uniformly accelerated motion, meaning speed increases proportionally with time, then the distance traversed increases as the square of the time. He uses Euclidean geometry, no calculus, ratios and proportions. He proves the odd number rule. He proves projectile motion is parabolic when you combine constant horizontal motion with accelerated vertical motion. And he acknowledges the idealizations. In reality, air resistance changes things. In reality, perfectly smooth surfaces don't exist. In reality, the Earth's curvature matters for long projectiles. But the idealized laws show what's underneath. Remove the friction, remove the air, remove the complications, and you see the principle. Inertia. An object in motion stays in motion unless acted upon by a force. An object at rest stays at rest unless acted upon by a force. Force changes motion. No force, no change. Galileo doesn't say it in exactly those words. Newton will say it that way in 1687 in the Principia. But it's Galileo's idea, built across 5 decades of thinking. Here's what makes this important. Galileo didn't just change physics, he changed how humans think. Before Galileo, the way you understood motion was, observe what happens. Accept what seems obvious, fit it into the philosophy passed down from authorities. Aristotle said, heavy things fall faster. Looks right. Don't question it. Galileo's method, observe carefully, measure precisely, isolate variables, imagine idealized conditions, use mathematics to find patterns, test predictions against new observations, accept that what seems obvious might be wrong. This is the scientific method. It's so embedded in how we think now that it seems trivial. Of course, that's how you do science, but in 1590, that wasn't how you did anything. Philosophy and natural science were the same thing. You reasoned from first principles about what must be true based on the nature of things. Galileo said, I don't care what must be true. I care what is true. Build experiments. Measure. Calculate. If the data contradicts the philosophy is wrong. And this got him in trouble, because the Catholic Church had tied Aristotelian physics to Christian theology. The earth at the center, unmoving. Heavy things seek their natural place at the center. The heavens are perfect and unchanging. This was doctrine. Galileo saying the earth moves, saying motion is relative, saying there's no difference between rest and motion, wasn't just wrong physics, it was borderline heresy. They forced him to recant, but they couldn't erase what he'd figured out, back to the mental process. How does a human brain go from seeing motion one way to seeing it another way? Galileo's notebooks show the struggle. He writes equations, crosses them out, rewrites, draws diagrams, erases, starts over. On folio 128, there's a draft proof from 1604 trying to derive the time-squared law from speed proportional to distance. He realizes later it's wrong, doesn't throw it away, leaves it in his notes. On folio 81, there's projectile data showing constant horizontal speed. He puts question marks next to numbers, circles some, crosses others out. He's seeing something that doesn't fit his theories, but he doesn't know what it means yet. On folio 116, he tests dropping balls from different heights with horizontal deflection. Measures where they land. The pattern is there. Horizontal distance increases with the square root of the vertical drop height. Why? Because vertical fall time is proportional to the square root of height by the time-squared law. And horizontal distance is proportional to time if horizontal speed is constant. So distance horizontal is proportional to the square root of height. The mathematics predicts it. He tests it. It works. Now he knows horizontal speed is really constant, not just a good approximation, actually constant in the idealized case. That's when the old framework collapses. If horizontal speed is truly constant with no horizontal force, then motion doesn't require force. Then force is not what causes motion. Force is what changes motion. This is the conceptual flip. And it happens slowly, across multiple experiments, multiple years, multiple failed attempts to make the old ideas work. Let's be specific about what had to change in Galileo's thinking. First, the idea that motion and rest are different kinds of things. That had to become motion and rest are the same state described relative to different references. Second, the idea that continuing motion requires continuing cause. That had to become continuing motion at constant velocity requires no cause. Only changes in motion require cause. Third, the idea that falling speed depends on distance fallen. That had to become falling speed depends on time falling. Fourth, the idea that all motion is either natural motion to natural place or violent motion forced by mover. That had to become motion is change of position characterized by velocity and acceleration, independent of categories like natural or violent. Fifth, the idea that mathematics describes idealized perfection that real objects only approximate. That had to become mathematics reveals the true laws that govern real objects once you strip away complicating factors like friction and air resistance. Each of these shifts is subtle. Each contradicts what seems obvious to your senses. And Galileo had to make all of them, not by being told they're true, by working through problems, getting stuck, finding contradictions, slowly realizing the old framework doesn't work and there's another way to see it that does work. That's the mental process. It's not a flash of insight. It's a grinding at which years-long struggle against your own intuition. If you value documented history of scientific ideas like this, subscribe. Comment your city. This is the second call to action reminder. Here's what Galileo's contemporaries couldn't see. When you watch something fall, your brain automatically constructs a story. Heavy object. Falling. Must want to fall. Must have gravity pulling it. The heavier it is, the more it wants to fall. That's Aristotelian gravity. Sounds right, looks right, fits the data you see with your eyes, except it doesn't. Galileo proved it doesn't with the inclined plane. When you roll different weights down the same ramp, they accelerate the same time to roll the same distance. The only difference is friction affects the light object slightly more because it has less momentum to overcome friction. In a theoretical frictionless case, identical acceleration, so heaviness doesn't determine falling speed. Then what does? Time. The longer you fall, the faster you get, at a constant rate. 9.81 meters per second squared on Earth's surface. Every second, your speed increases by 9.81 meters per second downward. That's acceleration, constant for all objects regardless of mass. Why? Galileo didn't know. He just knew it was true for measurement. Newton would later explain it with universal gravitation. Gravitational force is proportional to mass, but inertial resistance to acceleration is also proportional to mass. The two cancel out, so acceleration is independent of mass, but that's Newton in 1687. In 1638, Galileo just has the observation and the mathematics. All objects fall the same in a vacuum. Speed increases linearly with time. Distance increases with time squared. Projectile paths are parabolas. Horizontal motion is independent of vertical motion. And motion at constant velocity needs no force to maintain it. These are the pieces. They'll be assembled into Newton's laws, but Galileo carved them out of a world that believed the opposite. The other insight that's easy to miss, Galileo's use of idealization. He talks constantly about perfectly smooth planes, motion through a void without air resistance, or perfectly round balls. Critics say, but real planes aren't perfectly smooth. Real motion has air resistance. Real balls have imperfections. So how can Galileo's laws be true if they only work in conditions that don't exist? Galileo's answer, implicit in his method, the idealized conditions show you what the law is. Then you add back the complications. Air resistance is a force. It opposes motion. It causes deceleration. But if you know the law in a vacuum, uniform motion persists indefinitely. You can then calculate how much air resistance slows it down. Friction on a plane is a force. It opposes motion. It causes deceleration. But if you know the law on a frictionless plane, you can calculate how much real friction changes the result. The idealization isn't a failure to account for reality. It's a method to see through the noise to the underlying principle. Once you have the principle, you add the noise back in. This is how physics works to this day. Frictionless surfaces, point masses, perfectly elastic collisions, ideal gases. These aren't lies. They're tools to isolate the fundamental behavior so you can understand it before adding complications. Galileo pioneered this, and it's brilliant. Because without idealization, motion is a mess. Every case is different. Every surface has different friction. Every object has different air resistance. You can't find the pattern. But if you imagine away friction and air, suddenly the pattern is clear. Uniform acceleration, time squared. Then you say, okay, in reality, friction reduces that. How much? Measure it. Now you have a complete model. Ideal law plus correction terms. Before Galileo, natural philosophers didn't think that way. They tried to account for all the messiness at once and never found the underlying principle. Galileo's genius was knowing what to ignore temporarily so you could see what mattered. There were predecessors. It's not like Galileo invented everything from nothing. In the 14th century, Jean Buridan at the University of Paris developed the theory of impetus. When you throw something, you impart impetus to it. The impetus keeps it moving. Buridan said, without resistance, impetus would last forever. That's close to inertia. Nicole Oresme, Buridan's student, did early graphical representations of motion. Used geometry to prove the mean speed theorem. A uniformly accelerated object travels the same distance as an object moving at constant speed, equal to the average of the initial and final speeds. That's crucial for deriving the time-squared law. So Galileo had intellectual ancestors. Buridan around 1300 to 1361. Oresme 1323 to 1382. These were the Paris School of Physics. They criticized Aristotle. They proposed impetus theory. They laid groundwork, but they didn't have the mathematical tools Galileo had. They didn't have the experimental precision. They didn't take the final step to say, motion doesn't need force, and they were forgotten. Buridan's works were put on the Index Librorum Prohibitorum, the Catholic Church's list of banned books from 1474 to 1481. They survived in Eastern Europe, particularly Krakow, where Copernicus studied. So there's a chain. Buridan to Oresme, to the Polish universities, to Copernicus to Galileo. Each step closer to modern mechanics. But Galileo's the one who clinched it with experiments and mathematics that couldn't be argued away. The hardest part of Galileo's journey wasn't the math, it was the intuition. He had to train himself to see motion differently. When you watch a ball roll to a stop on a table, your instinct says, the ball stopped because motion naturally decays. That's Aristotelian. Galileo had to retrain himself to see, the ball stopped because friction and air resistance opposed its motion. Remove those forces, it wouldn't stop. That's not obvious. It's not what your eyes see. Your eyes see the ball stopping. They don't see the invisible forces of friction and air. So you have to imagine a world that doesn't exist, a frictionless vacuum. And ask what would happen there, and trust the mathematics to tell you. Galileo spent decades building that trust. Every time his equations predicted something and his experiments confirmed it, that was evidence the idealized model worked. The inclined plane experiments, rolling balls, measuring times. The data fit the time-squared law, evidence, projectile experiments, balls rolling off ramps, measuring landing distances. The data fit parabolic paths from constant horizontal speed plus accelerated vertical fall. Evidence, ship thought experiment, observing that motion below deck is the same whether the ship moves or not. Evidence, layer by layer. Experiment by experiment, Galileo built confidence that the mathematical idealization captured something real, that nature actually followed these rules, and the mess we see is just those rules plus friction and air. Once he trusted that, the old Aristotelian framework became unnecessary. He didn't need natural motion and violent motion. He didn't need objects seeking their natural place. He just needed force, mass, acceleration, and time. Those four concepts, related by mathematics, described all motion, simpler, more powerful, more accurate. That's why it won. Now, here's the thing that breaks your brain if you think about it too long. Galileo proved experimentally that inertia exists, but you can't actually experience pure inertia. Every motion you've ever witnessed has friction or air resistance or gravity or some force acting. There is no perfectly smooth surface. There's no perfect vacuum on Earth. So how did Galileo prove something that can't be observed directly? He proved it by showing that the deviations from ideal inertia could all be accounted for by measurable forces. Air resistance slows things down. Friction slows things down. Gravity pulls things down. In every case, remove those forces in your calculation and you get constant velocity. Add those forces back in, and you get the motion you actually see. So inertia isn't observed, it's inferred. You observe motion with forces. You calculate what forces are acting. You subtract those forces mathematically. What's left is inertia, constant velocity motion with no forces. You never see it pure. But the mathematics says it must be there underneath. And every experiment confirms that when you account for forces correctly, assuming inertia is the baseline, the predictions match reality. That's profound. Galileo discovered a principle by proving it's what you'd see if you could remove everything that hides it. That's a level of abstract thinking that didn't exist before him in physics. Philosophy did abstraction. Mathematics did abstraction. But applying mathematical abstraction to physical experiments, to reveal hidden principles that govern observable reality, that's new. That's Galileo's legacy. We end with a late detail that reframes everything. In 1642, Galileo died under house arrest at age 77. His Discorsi had been published 4 years earlier. His work on motion was complete, but there's a fragment that didn't make it into the Discorsi. A sixth day that he wrote around 1638 to 1639, but never finished. It was published posthumously in 1718. In this fragment, Galileo works on the force of percussion. The force of impact when a falling object hits something. He's trying to measure it, quantify it, understand why a small object falling from great height hits with enormous force. He never solves it. The mathematics isn't quite there. That problem will take Newton's second law and the concept of momentum to fully resolve. But what's remarkable is Galileo, at age 74, 75, nearly blind, under house arrest, forbidden to publish, is still working on the edge, still trying to extend his theory of motion, still refining his understanding of how force and motion and impact relate. He never finished because he ran out of time. But the fragment shows his mind was still fighting for clarity until the end. He died having rewritten humanity's understanding of motion, having proven that force causes change in motion, not motion itself, having shown that mathematics reveals the laws nature obeys, having taught us to isolate variables, idealize conditions, and test predictions, having built the method that would become physics. And he did it by learning to see a falling rock and think, it's not falling because it's heavy, it's falling because gravity is accelerating it. And if I could turn off gravity, it would keep moving forever in whatever direction it was going. That thought, that strange, almost counterintuitive, mathematically rigorous thought, changed everything. The mental process Galileo went through to understand inertia was the process of inventing modern science, and we're still using his method 400 years later. Final detail. There's a manuscript page in Florence, folio 116. Galileo rolled a bronze ball down an inclined plane, deflected it horizontally at the bottom, measured where it landed at different heights. The data points are still visible on the page. Ink on parchment from around 1608. Numbers written in Galileo's hand. Circles around, results he found important. This page was unknown to his contemporaries. He never published this experiment. He used its results to understand projectile motion, but the raw data stayed in his notes. It wasn't rediscovered until Stillman Drake analyzed the manuscripts in 1973 and published his findings in ISIS. So for 365 years, this piece of evidence that Galileo experimentally confirmed constant horizontal velocity sat in a drawer. When Drake analyzed the numbers, they show exactly what Galileo needed them to show. Horizontal distances proportional to the square root of vertical heights, which means horizontal velocity, constant, vertical velocity accelerating. The principle of inertia captured in ink and old data from an experiment nobody saw. That's the footnote. The ideas that changed the world were built on measurements written down in private notebooks, worked out through trial and error, refined across decades, and only fully revealed when an old man under house arrest decided to publish everything he knew before he died. Galileo's mental process to understand inertia wasn't a lightning bolt of genius. It was stubborn, grinding work against every intuition nature gave him, and it worked. We see motion his way now. Objects in motion stay in motion. That's not obvious. That's learned. And Galileo learned it first.